Okay, I think we may start. Well, good afternoon, everyone, and welcome to today's EPICURE webinar on computational rheology with OpenFOAM from code development to industrial application. We are delighted to have with us as we explore the Institute of Polymers and Composites and show how customized OpenFOAM solvers support predictive modeling, process optimization, and polymer processing equipment designs through practical examples. Today, presenter will be Professor João Miguel Nóbrega, an associate professor in the Polymer Engineering Department at University of Minho, and a member of the Institute for Polymers and Composites. His work focuses on polymer processing, material rheology, and product development, with a strong emphasis on computational rheology and advanced simulation tools on OpenFOAM. He is also actively involved in the OpenFOAM community, serving as editor of the OpenFOAM wiki and OpenFOAM journal. Before, I want to thank Miguel for being here with us today, and before passing the word to Miguel, I would like to inform you all that you can and should interact during the presentation. To do so, you can use the chat to share your questions. During the presentation, we'll try to not interrupt Miguel, but in the end, we will provide some minutes to discuss and all the questions, so you can interact directly with Miguel if needed. We'll be monitoring the chat activity and ensure that all questions will be answered in the end. Okay, just before start, we'll please ask you to keep your microphone muted during the session to prevent background noises, as the session will be recorded for later be sharing with you all. And with this, I pass the floor to Miguel, and once again, thank you for being with us today. So,
thank you, Antonio. I'm sharing my screen. Can you see the screen?
Yes, we are seeing, not in presenter mode, but we are seeing your screen. Yes.
Now in presentation mode.
Yes.
Yeah. Okay. Perfect. So, thank you. First of all, thank you for the invitation. It's always a pleasure to talk about our work. I say our because, what you're going to see is the work that has been done in the framework of the Computational Rheology group from IPC, as Antonio just mentioned. It's a team that develops, works on computational modeling and simulation. We belong to the University of Minho in the framework of the Institute for Polymer and Composites, and I also have a connection with PIEP. PIEP is our interface to industry. So it's a private company that is independent of the university. The university is one of the associates. There's a number of associates. It's located near campus to have a strong interaction with our department, and that's how we interact with the industry. And according to the invitation, I will try to give you an overview of what I've been doing in the area of computational modeling, especially done or mostly done with OpenFOAM computational library, and I'll try to explain why we use OpenFOAM. And I'll cover in the presentation both more applied research, so works we have been doing with different companies from all over the world, and some more scientific based work that is related to code development. I'm not sure I'll be able to cover all these topics, but after the presentation, I'll share the slides. And if you have any questions, I'm obviously available to interact with anyone. So, as I mentioned, I will initially try to explain why we have been using OpenFOAM, introduction to OpenFOAM for those of you who are not familiar with OpenFOAM. Then I will present some industrial applications. Some of them you would expect us to work with because we are a polymer engineering department or an institute for polymer and composites. We work exactly in this area, but others, for instance, like pacifiers, this is not very common. But we are covering these topics among others, and then some developments we have been doing in terms of numerical solvers that are available in OpenFOAM. Quickly mention some recent works and ends with the conclusion. So, first of all, OpenFOAM, for those of you who are not familiar with it, is open source computational library. It's available. You can download it and start using it immediately. It's programmed in C++. That doesn't mean you need to know C++ to use it. To develop it, you must be familiarized with C++. It follows mostly the finite volume method to solve the governing equations or the partial differential equations that govern the phenomena that is being modeled. Uses unstructured meshes, so is able to deal with complex geometries. It includes mesh generators, so it's able to deal and combine different phenomena, multi-physics modeling, multi-phase modeling. It has a number of features implemented, like fluid structure interaction, able to deal with multi-phase Eulerian, Lagrangian. One great advantage of OpenFOAM is it's parallelized. So, and I will show you some concrete examples where you can take advantage of HPC systems and with the benefit of the calculation time, obviously. And OpenFOAM has already, when it's downloaded from the internet, you have already a number of solvers. Fluid flow, compressible and incompressible, turbulence, combustion. Then it's possible to also to have particle tracking flows, so Lagrangian meshes, also molecular dynamics, electromagnetics, anything that is ruled by partial differential equations, OpenFOAM can deal with it. I would like to give you a perspective of the impact of OpenFOAM nowadays, and I omitted the numbers on purpose, but this is the evolution of OpenFOAM on the last 7 years. And this is the downloads that OpenFOAM got in SourceForge. The statistic is available. You can go there and check by yourselves. But it has you agree with me? It has a significant evolution. It even had an overshoot, and then now I believe is reaching some stable values. And you can see now the numbers. In 2023, OpenFOAM got about 11 million downloads. Now we're getting stabilized to 9 million downloads. I don't know, like it's quite difficult to anticipate the evolution, but the numbers are clear. There is interest in OpenFOAM. There are a number of persons using OpenFOAM. And when I say number of persons, it's covered, it's done, and it's being used all over the world. Everywhere you can find persons downloading OpenFOAM and working with OpenFOAM different places. Obviously, there are the expected number of users. US has a huge number. France has been using a lot of OpenFOAM, or the number of downloads they are getting is quite high. But you see users everywhere. And in 2025 reached about 8.8 million downloads. Give you a quick overview of our when I say our University of Minho Computational Rheology group, or Computational Rheology lab at University of Minho. So before OpenFOAM in 2014, it's when I came across OpenFOAM, and I was developing my own numerical modeling software, in-house developments. And if you have been used to do it, it's quite difficult to handle to keep these softwares and to pass it from persons from one person to other persons, and to keep on developing. And in 2014, I came across OpenFOAM on the exact week before the OpenFOAM workshop. OpenFOAM workshop is the largest event related to OpenFOAM. Joins developers, users, new users, old users, experienced users, and I was so excited with the possibility that I sent them an email asking to present something. And in that event, I presented a poster that was not about OpenFOAM, because I was not able to I didn't use it before. I just knew about OpenFOAM the week before, but the poster was what I plan to do with OpenFOAM. It was quite nice, the event. I had a lot of interactions with different persons, and in fact, 2 years after, I was organizing the OpenFOAM workshop in Guimarães. So they really saw I was motivated to use OpenFOAM, and I was invited to do it. In between, I started the Portuguese OpenFOAM users, and I organized the first FOAM FPT meetings on the Portugal. That's after 2016 evolved to FOAM Iberia. That is a group in which we have yearly events and joining the communities from Portugal and Spain using OpenFOAM. Then I started contributing to the technical committee for documentation and tutorials. The book of this conference has about 2,000 downloads in Springer, another nice number, and we have the OpenFOAM journal that has about 4,000 views per month. The last 2 months, the numbers increased quite a lot, and I'll show those numbers at the end of the presentation. In 2023, I hosted the FOAM Iberia meeting, the annual FOAM Iberia meeting, and the good news is that this year we'll be hosting again in Guimarães the OpenFOAM workshop that we expect to be a major event in the OpenFOAM community. Some examples of calculations you can make with OpenFOAM right after downloading it. So these are tutorials you can use. One that is directly integrated in OpenFOAM, the fluidized bed, where you have particles moving, interacting, colliding, and interacting with the surrounding fluid. And the solid mechanics, in this case, is a tool that doesn't come directly with OpenFOAM, but you can download it. It's the Solids for Foam toolbox, that is developed by a large group of persons as well, but the major developer is Professor Philip Cardiff. You have the links here, and you can check all this information. These slides illustrates for me the biggest advantage of OpenFOAM is the capability of programming and adapting OpenFOAM to your own needs, and it's done in such a way that the syntax that is used to solve equations is quite similar to the actual equation that governs it. You agree with me for sure that there are close relation between these instructions that are placed in the code with the actual terms, and it makes the code quite readable, allows us to easily, in an easy way, it's never easy, but in a straightforward way to understand what is programmed and adapt it to your own needs. So from now, I will cover a few. As I mentioned, I will cover a few of industrial applications we have been using OpenFOAM. So the first ones I did was related to design of profile extrusion dies. So the extrusion die, if you are not familiarized with these polymer processing techniques, the purpose is to manufacture profiles. Profiles is plastic parts with constant cross-section. So the material is placed here in this upper, then it's melted, and the extrusion die is somewhere over here, and it shapes the profile. Then it has to be cooled down in the cooling system. Then there is a cool-off that pushes the material at a certain specified velocity, and then there is a saw that cuts the material. The most difficult, or one of the difficulties of designing profile extrusion dies is flow balancing, because most of the profiles have different thicknesses, and if no care is taken, then the velocity, the material does not distribute properly, as you can see in this movie, so cannot produce the actual profile. In order to obtain the profile you need to balance the flow, and this is an example of a balanced flow of the same tool. This is the exact same tool, same geometry, but with different flow channel geometries. One important information is in most of the slides you'll see publications that are related to the information I'm sharing. So you can find additional details about this in these publications. Okay, in order to do it, in order to solve this problem in OpenFOAM, we need to add to the regular fluid flow equation, governing equations, that is the momentum and the mass balance equation that is converted due to the formulation into a pressure correction equation, but we need to add the energy equation. And this is the energy equation. This is the syntax of the equation added to the code. Again, I believe you agree there is a clear relation between these terms, and the equation we are trying to solve. This is one example that we work with Soprefa. Soprefa is a company from Santa Maria da Feira, is a city, I would say nearby, 1 hour from Guimarães, the place where I live. And they are specialized, or they used to be specialized in profile manufacturing, because currently they belong to another company and they do the same, but the name changed. Nowadays is CGA Plast. But Soprefa was trying to manufacture this profile, is a lead covering profile, and they were not able to do it by using a traditional approach, by trial and error experimentally, because the profile has different thicknesses, as I mentioned, 1.2 millimeters, 0.6 millimeters, 0.75 millimeters, and it was not possible to obtain, but they didn't manage. So we used the code. Okay, in this case, we had to fit the behavior of material to have an actual constitutive model that is used in the code. And in order to balance the flow, what we do, we divide the cross-section into different elemental sections. This is, and then we quantify the flow distribution through an objective function. The purpose is to have all terms of the objective function equal to 0. This is not possible in a real profile, so we want to get as close as possible. And if the terms are far away from the 0, means the flow is expected to be unbalanced. We created the code, we did a number of manual trials, and we were able to get the actual calculation and obtain the desired profile. More related to HPC, we recently, in the framework of a European project, we made the process automatic. So making automatic design. Automatic designs means have a software to generate the geometry, a trial geometry. Then we
Sorry to interrupt you, Miguel. I don't know if we are only seeing your PowerPoint without any slide. I don't know if it was on purpose or...
No. You can see the slide?
Only the initial slide.
This is something is wrong with the. Let me share the screen, the actual screen. No, not this one. Can you see the slide? Oh, okay. Oh. Can you see the screen now?
No, I see. We see your screen now.
Can you see now the?
Yes, we now are seeing a machine. Yeah.
Okay, so you missed a lot of details. But then I'll share the slides
on that one with the graphs. Yes, we lost you.
Sorry. Were you able to get this one?
No, these ones no.
Okay.
Ones before. Yes, there. Almost there.
Okay. So it was in this case the balanced. Then we're able to optimize it and manufacture the actual profile. That was it is what I was saying. Then here it's the coupling with HPC. So in order to couple it, we need to have a geometry generation software. Then through a cloud system, we're able to communicate with the HPC system that runs OpenFOAM to make the simulation. And we coupled OpenFOAM with Dakota in order to, Dakota is open source optimization software, in order to propose a new geometry and make all the calculations. Here, it's a summary of different profiles we tested in the framework of that project. And two relevant numbers are the number of trials, so above 660 trials in the framework of 15 hours. So it means the computer was working continuously to look for an optimized solution. This is the actual cost of calculation time we used for different profiles, and the numbers are similar. It depends on the profile we're trying to optimize. Might be easier or more difficult, but we're able to obtain all this information into a cost that is quite nice. And we showed in the framework of that project that it allows the reduction of the time to market, the amount of material spent in trials and errors, and the overall savings in tool development. That had a huge impact. Nowadays, Soprefa is not Soprefa anymore. Soprefa was acquired by CJ Plus, and we have a PhD in this area, further improving the code, working with CJ Plus. We also work with Michelin, the tire manufacturer, mostly with the team from Clermont-Ferrand, is the research team from Michelin, and we have been showing with them that it's possible also to optimize in this case it's a different geometry, but okay, we have different restrictions here, upstream restrictions, and it's possible to optimize the profiles that they manufacture also in an automatic way. Also, Michelin, we started a PhD beginning of March to further explore these capabilities with numerical modeling and optimization. Here, I will not mention the details. This is the different trial and error approaches. In this case, we implemented a different optimization approach, is the Bayesian optimization. Again, you can see the paper related, illustrated here. Okay, the purpose is to reduce the objective function again, as we did with the previous one, and we're able, even with this profile, able to further improve the performance of the tools. And okay, you can see here from the velocity distribution that okay, the initial trial was not that good. The last trial is much better in terms of flow distribution. Since we have capability to do heavy calculations by having access to HPC, we have been trying also the advantage of being more accurate in terms of calculation. And this is one of the examples where we used a tool. In this case is like an extrusion die, is the actual tool that manufactures the profile. And in this case, the purpose was to model not just the flow channel, that's what we do usually, but to model everything. The behavior of the metallic tool, the control of the temperature control of the system, and that allows, we expect us to be more accurate in terms of calculation, and this would be feasible some years ago, where we didn't have access to high performance computing systems as the ones we have nowadays. So this is the inner part of the tool. So here there is a thermocouple that controls the temperature, a heater that connects based on the value read by the thermocouple. There are two heaters and two thermocouples. I will not get into these details, but to give you an idea that we are able, by doing this, we're able to explore different ways or more precise ways of modeling. And the purpose was, okay, figure out if there is a difference. What would happen if we are more precise in terms of calculation? In order to do it, we adjusted a solver from OpenFOAM in order to make a few modifications, and it created a new boundary condition in order to mimic what happens with the thermocouple and the heater, and we compare different approaches. Again, okay, here is the unsteadiness of the process that is illustrated, where we have the reading from the thermocouple, in this case virtual reading, and the activation or deactivation of the heater, and the process becomes quasi steady state, but it's not steady state because there are oscillations motivated by temperature, and we figure out that there are some options that are appropriate, but there are other options or there are other measurements we get that are not so accurate. In this case, there is a significant difference in terms of pressure drop by using these the more accurate measurements. In terms of the law distribution, we see also some features, and in terms of the objective function, there are even different signs. So depending on the approach we use, we might be on the opposite side of the correction. So we could be misled to perform corrections that are not required in the tool. We also have been using to model the second part of the extrusion. system, the calibration, in this case, cooling, so a metallic part, a profile that is cooled down, and the main unknown here is where to place the cooling channels. And we showed, again, by using coupling it with Dakota, we showed that there are the solvers or the optimization framework is able to identify good solutions. Also test it with different calibration units. In this case, we are cooling the material in different calibration units, and we can see here the dots are the measurements and in different locations, and the calculation follows. It's not exact, but it follows the trends that we measure experimentally, and obviously gives a very good support for design purposes. Also, work we've been developing for the past years with Logoplast. Logoplast is a packaging manufacturer that started in Portugal, but nowadays they have factories all over the world. And the purpose was to model the extrusion blow molding process. Extrusion blow molding, you start by producing a tube. The tube is clamped in a mold, is inflated, cooled down, and at the end we get the package. Why we did this? Because there are softwares that are able to do some of the parts, but in separated manner. And we want to work on optimization, and in order to do it, we need to model the full process. We started by the clamping and inflation. We used linear elastic and hyperelastic models. We also tried more complex models, but those models were taking much more time than required to perform the calculation. So we have been proceeding mostly with hyperelastic models. What we do here, what we implemented here, is something that solves the Newton's second law. Times mass acceleration is equals the sum of the forces. And by doing this, we're able to simulate what happens in extrusion blow molding, so the part of the blowing itself. One example, a complex container. We have the molds. This is the inputs we place in the code, the parison, the actual material tube that is formed, and we can see here the evolution. So the mold is closing. The mold is closing, and then it's blown, and we get the final container. By doing this, we can monitor, for instance, the thickness distribution and proceed accordingly in order to correct. What do I mean proceed accordingly? When manufacturing the different tube, it's possible to have a tube with different thicknesses along the length. So along the length, we can have different thicknesses. The issue is that, okay, which should be the appropriate thickness of each of these layers in order to get the distribution, the final thickness distribution we want. In order to do it, we did the same. So we model, we do optimization, and this is one example. Again, I will not cover in detail. The example is a ovalized container that is not easy to manufacture experimentally. We can see, I will speed up the movie. You can see that the thickness distribution, there is a reduced thickness near the corners we need to be able to solve this. And by doing different iterations, by correcting the process, we're able to obtain the appropriate thickness distribution. We also model the initial part, the extrusion part, and by moving the mandrel, adjusting the thickness, so we're able to do it. And again, we used OpenFOAM solvers and adapt OpenFOAM solvers. In this case, we use the viscoelastic solvers that are available in Rheology. Is also a nice feature that is available, is publicly available to use with OpenFOAM. We're able to model using moving meshes from OpenFOAM. We're able to model the adjustment of the thickness that takes place along the process by adjusting, by moving the mesh. And okay, this is a typical run of the tube manufacturing. I will just stop on the moving mandrel part, this one, where we can see that the inner mandrel is moving, and we can adjust the thickness in accordance. So, and we're able also to link the different stages by mapping the inner and outer surface of that tube, the perisome, into an STL and calculate the thickness, and that information is sent to the optimization. And you can see here a recent work. In this one, I'm missing the publication, but there was a publication that appeared last year where we showed the experimental validation of the code predictions that are quite well aligned with reality. Well, also have been working in injection molding, and injection molding is one of the most widespread manufacturing process for plastics. So we have a cavity in which the melted material is injected, and at the end it cools down, and we get the different geometry. We're able to model the process. In this case, we used OpenInch Mold Sim, is a solver that was not developed by us, but is available at the internet. We ported it to recent versions of OpenFOAM, and that allowed us to validate. And we did it by comparing with standard softwares that are available in the market. In this case, the OpenFOAM calculations are quite nice and aligned with the software, with that benchmark software. The main difficulty is calculation time, but again, we're able to get similar calculation times by resorting to HPC systems. We have been using with shoe industry in different places. We're also been using the solid mechanics solvers to design different parts. In this case, this is for a safety shoe. This is the tip of a safety shoe, and this is the test done for compression, experimental and simulation that are quite well aligned, and also impact tests. So, and the differences were quite nice. This is also a recent study we made with Pro Calçado, a shoe manufacturer, in this case a shoe sole, in order to make it more comfortable. So we helped them designing these dampers in order to obtain a comfortable shoe. We were able to obtain different behaviors, have shoes or soles for different persons with different weight, and by using additive manufacturing, we're able to manufacture molds that would allow to obtain a shoe sole with different configurations. Also, I mentioned before the pacifiers. In this case, we have been working with Nuke, or the Mappa is the manufacturer of Nuke brand pacifiers. And here the purpose was to model the full palette, the full process with the tongue, the pacifier, the palette, different tissues, even the inner teeth. And what we developed allows to have a detailed overview of what is happening inside the mouth cavity. The tongue that pushes the pacifier, that pushes the palate, and then we're able even to calculate the displacement of the teeth. Okay, you cannot see it directly, but by increasing 100 times, we're able to see the impact on the teeth tissue, and we can compare different pacifiers. This has been a huge impact in the pacifier world, and we have been able to quantify and compare different pacifiers. And this was a topic of a press conference given in 2022. Concerning, and I will have to do it briefly, numerical developments, we have been working with implementing in OpenFOAM different capabilities. For instance, new solvers, in this case, the integral viscoelastic solver, using approaches that are available in internet. We have been doing it with a person that is specialized in these kind of approaches, is Manuel Silvino Araújo from Brazil, and he had already a background in this area, and we work together in order to implement this in OpenFOAM. Okay, this is one of the main governing equations, the actual code. Again, the similarities between the different terms that are given, and we're able to validate. You can see from the graphs, I will not get into details again, but you can see from the graphs that the numerical trends are in line with the theoretical evolution. And by comparing different codes, we also did comparison with experimental measurements and for different quantities of the channel, and were able to replicate the experimental measurements for different features. We also implemented new codes. In this case, there was a problem in the original viscoelastic solvers available in OpenFOAM, that was decoupling between fields. And in this case, I would like to point out that, okay, we follow what we call the both sides diffusion approach, where the equation is a bit changed by adding in two sides of the equation a diffusion term that stabilizes the calculation. But by using it, the problem was that decoupling problem was not solved. So we proposed a new approach that required just the change of one line of code. This was the line that was changed, that instead of computing the Laplacian, we compute the divergent of the gradient of the velocity field. And this is the only line of code that was changed. And the problem, and this gives us a large stencil, so a large number of cells involved in one equation, and we got the problem of decoupling solved, but just by changing that line in the code. And we showed that we're able to replicate whatever was available in the literature. Some recent work as well, in this case, is published in the OpenFOAM journal. So we implemented in OpenFOAM the capability of predicting the evolution of fiber orientation. Fibers are relevant. Fiber orientation are relevant in the world of plastics, high performance plastics, when we want to obtain high performance tools, and the orientation of fibers has a huge impact on the mechanical behavior. And we created a solver that is not an independent solver, is a plugin that is connected to any solver of OpenFOAM, can be connected, providing it has the velocity. And by doing that, we can predict fiber orientation. Again, this was published last year. In this case, in the OpenFOAM journal, these codes are freely available to be downloaded. By doing this, we can predict fiber orientation in many areas. I will skip that one, but it's tools for code validation, also available in the OpenFOAM journal. We did it following the method of manufactured solutions. Some ideas of recent work. So I've been working in additive manufacturing. In this case, 3D printing of plastics at the bottom, cementitious materials on top. We are using moving meshes that are available in OpenFOAM and adding some features to be able to predict temperature fields and other features. Also working with SLS, also additive manufacturing, in order to predict the coefficients of particles, phase change, and so on. Recent European projects where we have been involved in order to improve the calculation of OpenFOAM. In this case, we in order to model viscoelastic flows, we tried to couple solvers. So instead of solving each equation separately. We solve everything at the same time. That is allowed even with the huge memory restrictions, and we're able to obtain, using very high core counts, speed ups of about 3 times in terms of calculation when compared with the segregated approach. We've been working also with a company that has a simulation company in order to develop new capabilities and new features for injection molding. This is the code. This is the book I mentioned at the beginning, but with more recent numbers. These numbers are from last Monday. Just to finish, if you are curious about OpenFOAM, there is a wiki where you can learn how to use OpenFOAM. There will be the OpenFOAM workshop in Guimarães this year, end of June, beginning of July. In the framework of OpenFOAM, this is one of the first times I'm talking about this. There will be a hackathon about OpenFOAM in order to connect OpenFOAM and Guimarães. Guimarães this year is the European Green Capital, and we want to use OpenFOAM to give some better understanding about sustainability, and in this case there'll be a hackathon and a challenge regarding mobility habits, mobility approaches, how they can impact the air quality in the city. And we expect also to have in 2026 from Iberia in Madrid, but there are still no dates yet. Before finishing the OpenFOAM journal, we started OpenFOAM journal in 2021. We're almost reaching 50 papers, but the papers in OpenFOAM journal are quite different from what you see in general journals. So anyone that publishes an OpenFOAM journal publishes also the case files and the code, so you are able to replicate everything you read in the journal. There is a discussion forum associated to each paper in order to promote the interaction between the readers and the authors. And these are the numbers, our current numbers of OpenFOAM journal. So above 1,000 subscribers in the journal. In LinkedIn, our channel has above 10,000 followers. We are about 100,000 views in our YouTube channel. And nowadays, the last 2 months in the OpenFOAM journal, we had above 10,000 views. So this shows the interest and the motivation that this field has. Obviously, as I mentioned at the beginning, this work is done by a number of persons involved with different corporations, different ways to work together, and this allows us to make all these contributions. And before finishing, I want to highlight some of the persons that were in the past in the group that nowadays are doing very nice work somewhere, and evolving with all the work, all the knowledge we developed together, and they are now working on contributing in other places. And this is, for me, a very important sign of the impact, the measurement of the impact of our activity. And this is it. Sorry for the extension and sorry for the problem with the slides, but something is wrong today with Teams, and I know why. So, Antonio.
Okay, Miguel, thank you very much for your nice presentation. I now open the floor for some question. If someone has any question to ask Miguel, or I may start the questions. But, you have presented lots of interesting works in here. But
we have a request.
A question, Alexandros.
Hi, thank you. You can ask. I can ask later. It's fine.
No, just Go ahead.
Thank you, Professor Nobrega, for the very interesting presentation. I think I've seen a version of it at the Institute of von Karman Institute of Fluid Dynamics last year.
Yes.
Always very interesting. Back then, I also told you I'm also a doctoral student in Germany. I work with filled polymers, and I use OpenFOAM for simulations of dyes for those filled polymers.
Oh, nice.
I would like to ask you, because this is the problems I have all the time. Do you mesh with Gmesh or CFmesh or snappy hex mesh? Because I have I cannot even begin to describe how many hours I've spent meshing.
Mesh is always a problem when we are designing tools. Most of the times we use CFmesh, Cartesian mesh. In some cases, because we don't have yet access to CFmesh Plus. CFmesh Plus is a huge, powerful tool. Hope to have access to it soon. But in some cases, like the one I showed with the metallic part and the flow channel, modeling everything at the same time, in that case we use SnapX Mesh. Sometimes when the geometry allows, we used Gmesh to have more control on the mesh. But a straight answer is most of the times we use CFmesh. CFmesh is, I believe, the tool that gives us for this application the most flexibility and is quite easy to use. You can start using CFmesh by specifying the mesh size, and then it generates a mesh, providing you have a good STL. In some cases, you need to go back a bit and correct the STL in order to avoid problems you have on the mesh generation. But I agree with you. Mesh in complex problems is it's a huge.
And one
one
last question. You opened in your presentation about a viscoelastic solver that you developed. Is there any way for me to get access to that? Is it available?
No, I mentioned two alternatives. I didn't mention in detail, but when I mentioned the other one, I omitted. In foam extent, you have in the distribution the viscoelastic solvers. They are available. The other option is to use Rheology. Rheology is one of the best computational libraries for viscoelastic calculations. The main problem of the Rheology is that it was developed by Francisco Pimenta, and he left the area, is now not working anymore, so it's not available on the most recent versions of OpenFOAM. But please contact me, and we have been porting it. We have been porting it to most recent versions, and we can discuss and work together in that.
Thank you very much. Thank you very much.
It's something we can do together if you are interested, and I'm happy you are interested, because we are working in an area when there are not many persons in OpenFOAM working in the same field of polymer process. So we can do it together and try to advance faster the field, because
thank you very much.
There's a huge room. If you are interested in the area, okay, the fiber orientation is available in the OpenFOAM journal. It was published in the OpenFOAM journal. We'll have soon the injection, the new generation of the injection molding solver. It's IMFOAM. It was developed in the framework of Bruno Rameau, a PhD. We just sent last week the publication, and we hope to have it accepted and have the repository public soon. It will be made public, and everyone to promote the further developments and the use of these tools in the field.
Yeah. Thank you very much.
Okay.
I will contact you, of course. Thank you very much for the offer.
Please do it, and we can for sure work together and proceed in this area.
Thank you very much for your question. I don't think there is any more questions. I also want to thank you, Miguel, once again for helping us in spreading the usage of OpenFOAM and the HPC relation. Use the OpenFOAM.
Okay.